Hello, in this video we will continue the explanation of the fourth part of the electronic voltmeter, which is the computer system. As we mentioned earlier, the computer system will count the number of pulses that resulted from pulse generator during discharging of the capacitor. So, the time of discharging of the capacitor will be equal to the number of pulses resulted from the pulse generator during discharging divided by the frequency of the pulse generator. As we know that Vc is equal to Vc initial multiplied by e to the power of minus t divided by gamma, and Vc is the minimum voltage required to make the transistor work, and it's a constant value. And for the simplicity, we will suppose that Vc is equal to 1 volt. By putting this value in this equation, we will get Vc initial, which is equal to e to the power of t divided by gamma, and both these values are for discharging. So Vc initial is equal to e to the power of number of pulses divided by the frequency of the pulse generator, and the whole value will be divided by gamma of discharging. And Vc initial, which is the voltage that results from charging the capacitor for 30 seconds. So Vc initial is equal to V, which is the voltage that we want to measure, multiplied by 1 minus e to the power of minus t divided by gamma, and both these values are for charging. So V is equal to Vc initial divided by 1 minus e to the power of minus t divided by gamma. By putting this value in this equation, we will get V, which is equal to e to the power of number of pulses divided by the frequency of pulse generator, and the whole value divided by gamma, and the whole numerator will be divided by 1 minus e to the power of minus t divided by gamma. And for the simplicity, let's suppose that f is equal to 30 Hz, gamma of discharging is equal to 30, t of charging is equal to 30 seconds, gamma of charging is equal to 3. So V is equal to e to the power of 1 divided by 900, and the whole value will be divided by 1 minus 1 divided by e to the power of 10 multiplied by e to the power of number of pulses. By the simplification of the equation, we will get that V, which is equal to 1.002 multiplied by e to the power of number of pulses, and the computer system will calculate this equation. The algorithm that's required to perform this equation is this. First, V is equal to 1, E is equal to 2.7, C is equal to 1.002. Then V will be equal to V multiplied by E, and that means when the first impulse passes through the comparator circuit, E will be multiplied by 1, and when the second impulse passes, E will be multiplied by itself, and so on. And that will follow the mathematical rule that says during the multiplication, the powers are summed together, providing that the bases are equal. V will be equal to V multiplied by C, and finally, the output from our algorithm is V. The data path that is required to perform this algorithm is this. It's basically composed from 8 bits multiplexer, which is 2 to 1 multiplexer, 4 by 8 bits register file that is modified as we mentioned previously by the removal of the third and the fourth registers and putting constant values in the third and fourth locations respectively. 8 bits multiplier circuit added together with 8 bits pass A circuit, and that circuit will pass the value in the port A without any change, and a gate that controls the output from our data path. Our data path also contains a feedback loop, and that loop will return the value resulted from the multiplication to the multiplexer, and that's to repeat the multiplication operation for variable number of times. The control signals that are required to control the data path are shown. S is to pass 1 or the value from the feedback loop through the multiplexer to the register. WE is to enable the decoder of writing, and WA is to write a value in the first or the second locations of the register file. RAE and RBE is to enable the decoders of reading through port A and B respectively. RAAO and 1 are required to read a value in one of the 4 locations of the register file and pass it through port A, and that's similar to RBAO and RBA1. M is to choose either the multiplication or pass A, and OE is to enable the output from our data path. Before we proceed in our explanation, there is 2 facts that we should mention. The first one is that pulses through the comparator circuit will meet together with pulses from the clock of our data path in this AND gate, and the clock should have the same frequency and phase of the oscillator, so that the resulting signal, which is N, will be equal to 1 whenever there are pulses through the comparator circuit. The second fact is that this signal will pass through this time-dependent switch, and that switch will allow this signal to pass through it after 30 seconds, and that means it will allow it to pass at the end of charging of the capacitor. So, as this diagram shows, which is called the next state diagram, and that represents the states that is needed to perform our algorithm. The algorithm needs 4 states to be performed, beginning from the first one and ending in the last one. The first one is coded by 00 and the last one is coded by 11. The first state will return to itself when n is equal to 0, and that means it will return to itself when there is no pulses from the comparator circuit, and during that time the capacitor of the base circuit is charging, and it will go to the next state when n is equal to 1, and that means it will go to the second state when there is pulses from the comparator circuit. The second state will return to itself whenever there is pulses, and will go to the third one when there is no pulses. The third one will go to the fourth one unconditionally. In the first state, the operations that will occur are V is equal to 1, E is equal to 2.7, C is equal to 1.002. In the second state, the operation that will occur is V is equal to V multiplied by E. In the third one is V is equal to V multiplied by C. And the last one, the output of V will occur. As a simplification of this diagram, we will use this table, which is called the next state table. It's composed from 3 columns. This column is for the current state, and these 2 columns are for the next state. As you see, the first state, which is coded by 00, will return to itself when n is equal to 0, and will go to the second one when n is equal to 1. The second state will go to the third state when n is equal to 0, and will return to itself when n is equal to 1. The third and the fourth states will go to the fourth state, whatever the value of n is. And we will use a D flip-flop so that the value of D will be equal to the value of Q next at the beginning of the next clock cycle. So, by using these two tables, we will get the values of QO next and Q1 next respectively. The value of QO next will be equal to 1 whenever Q1 is equal to 1 or n is equal to 1. So QO next is equal to Q1 or n. The value of Q1 next is equal to 1 whenever Q1 is equal to 1 or when Q1 is equal to O, QO is equal to 1 and n is equal to O. So Q1 next is equal to Q1 or QO and n bar. So the control signals are shown in this table. In the first state, S will put into 0 so that the value of 1 will pass through the multiplexer. And by putting WE and WA 1 and 1, the 1 value will pass to the second location in the register file. And these signals are all don't care. In the second state, the decoders of reading are both enabled, and the values in both the second and the third location will be read by port A and B respectively, multiplied to each other, returned back to the multiplexer, and by putting S equal to 1, it will pass to the register file. By putting WE and WA equal to 1 and 1, the value of multiplication will be stored in the second location. In the third state, the decoder of reading A and B are both enabled, and the values in the second and fourth location will be read through port A and B respectively, multiplied to each other and returned back to the same location. And during the last state, the decoder of reading A will be enabled, and the value in the second location of the register file will be read through port A, pass through the passer circuit, and then output from our data path. So that the value of S is equal to 1 whenever Q1 is equal to 0 and QO is equal to 1, or Q1 is equal to 1 or QO is equal to 0, so that it's equal to Q1 XOR QO. The values of WE, WA, RAE, RAAO, RBE, RBA1 are all equal to 1, and the value of RAA1 is equal to 0. The value of RBAO is equal to 1 whenever Q1 is equal to 1 and QO is equal to 0. The value of M is equal to the value of S, and the value of OE is equal to 1 whenever Q1 is equal to 1 and QO is equal to 0. So the next state machine that will control our data path is shown in this diagram. It's basically composed from two edge-triggered D flip-flop, variety of logic gates, and an inverter. The value of DO will be 1 each clock cycle whenever Q1 is 1 or N is 1. The value of D1 will be 1 whenever Q1 is 1 or QO is 1 and N is equal to 0. The values of S and M are equal to each other, and they will be equal to 1 whenever Q1 is 1 and QO is 0, or Q1 is 0 and QO is 1. The value of RBAO is equal to 1 whenever Q1 is 1 and QO is 0, and the value of OE is equal to 1 whenever Q1 is 1 and QO is 1. These values are always 1 and RAA1 is equal to 0. So, before I finish my explanation, I will mention that the numbers that we've used in this equation are just for the simplicity, and for better calibration of our voltmeter, the numbers that we've used in this equation should be replaced by more reliable numbers. So, that's the end of the computer system. Thank you for watching.